we've been talking about limits, and one of the things I said at the very beginning of all this was the whole thing that initiated the development of calculus was to answer a couple of questions. And one of those questions had to do with finding the slope of the equation of the tangent line to a curve. And I talked a little bit about how that represents velocity in the sense of a physics problem. So for today, I am going to pick up pretty much at that spot. Back in pre-calc, if you remember back in pre-calc, we talked about the difference quotient. And if you took pre-calc with me, we spent a lot of time talking about the difference quotient. Okay. This right here, this little image right here, represents how we find the average rate of change of a function. All right, if I were to draw a line between these 2 points, I think I have the pen up. Yes, I have the pen up. So if I were to draw a line between those 2 points, right, I would be looking at essentially the slope of that line, the change in the function over the change in the domain variable. All right, that is your definition of the slope of a line. And because that line crosses the function in 2 places, we call that a secant line. So the whole idea here with this process, and again, if you took pre-calc with me, we spent a lot of time talking about this. I don't know about anybody else, but the whole point here is I want to take this point that's up here, and I want to start moving it down the curve so that eventually it approaches this point right here. And when I do that, I will have a line that has rotated around and become tangent to the curve at that point. So if I take that secant line and I write the slope of it, okay, so that's going to be, again, the difference in the y's, which is f of x plus h minus f of x, all over the difference in the x's, which, because this is x and x plus h, the difference is just h. We get what you should recognize as the difference quotient, right? And the difference quotient represents the average rate of change of a function between 2 points. So when we looked originally at the beginning of our talk on limits at the, the train, right? The maglev train. We looked at the average rate of change between 2 time periods. I think it was like 2 seconds and 4 seconds. All right, and then we started on a numeric process of allowing that average rate of change, the distance between 2 and the other point to decrease to find the speed of the train. So we now have a way to talk about that process, right? In pre-calc, we talked about letting h approach 0. All right, so again, we have language for that now. It's called a limit. So if I add in front of this the limit as h approaches 0, right, I have a statement that allows me to now take the distance between x and x plus h and have it decrease, have it get smaller and smaller until x plus h approaches x, right? Which means my secant line is slowly rotating around that curve until it becomes a tangent line. So this right here, this difference quotient with the limit as h goes to 0, represents the slope of the tangent line to f, to the curve f at x, all right, at an arbitrary point x. All right, so that's how we go from an average rate of change, right, the slope of the secant line, to the slope of the tangent line by letting h approach 0. All right, now the slope of the tangent line is what we call the derivative. All right, so we have two concepts here. We have the average rate of change, right? The average rate of change. I don't know, I'm getting lag. Change of f is the difference quotient, f of x plus h minus f of x all over h. The instantaneous rate of change is what we get. There's an n in there somewhere. Is what we get when we let h approach 0. So that's when we take the limit as h goes to 0 of the average rate of change. All right. We define the derivative of a function as the instantaneous rate of change. Okay, so that's our first, well, it's not really our first. The limits were our first calculus concept. So this is our second calculus concept, but it's the more important of the two. All right, so we define the derivative of f to be the instantaneous rate of change of f. Rate, not rate. All right, so that's our concept for the derivative. Now, we need to talk a little bit about notation before I can start writing anything that looks like formulas. All right, so the main notation we're going to use, there's a few different notations for the derivative. I'm going to start out with the basic function notation for the derivative. And that is, we say the derivative of f, we write it as f with a little apostrophe up there. All right, that is read, you read that as f prime, f prime. All right, so now with our limit formula and this notation, all right, I can write f prime of x, the derivative of f of x, is equal to the limit as h goes to 0 of the difference quotient. Okay. All right, this is what we refer to as, I'll put a colon here. All right, this is what we refer to as the limit definition of the derivative. Give me 1 second here. I forgot to mute my phone. Okay. Throw that over there. All right, so anytime you hear that phrase, the limit definition of the derivative, All right, this is the formula that we're talking about. Okay. Now, in pre-calc, you would have gone through a process of learning how to calculate that. I'll do a couple because, again, not everybody took pre-calc with me. So I'll go through a couple of just like algebra tips for evaluating this. And in a little while, not today, but in a little while, we're going to learn some patterns that occur with different types of functions that will give us some formulas that when we see a certain type of function, we'll be able to apply a formula rather than having to always go back to the limit definition. The limit definition, though, is how we derive formulas. All right, so that's why we need this right now. Okay. All right, so let's look at some other notations for the derivative. All right, the most common one you're going to see me use is this one, f prime. All right, but if I don't have something written as a function, if I have it written as like a y equals equation, all right, then what I would write is this, the derivative of y with respect to x. And we write that as dy over dx. All right, and you may have seen this before written as the slope formula for a line, right? The change in y over the change in x, delta y over delta x. All right, depending on, your algebra teacher. All right, but dy dx is another way of writing the first derivative, the instantaneous rate of change of the function, y function of x. All right, so you'll frequently see dy dx equals f prime of x, all right, if I have y equals f of x. All right, you could also, over here, just see y prime, right? Y prime equals f prime of x. All right, same deal. All right, there is a third note, actually a fourth notation that we don't really use in Calc 1, but if you have to go on and take differential equations, you'll see it. If you go on to take Calc 3, actually 236 is Calc 2 here. All right, so if you have to go on and take 236, Calc 2, you'll get into taking derivatives of functions of more than one variable. All right, in which case you're going to see the notation capital D for derivative, and then an x right there to indicate the derivative with respect to x, and then usually a function name. All right, same thing, f prime of x. All right, so any of those notations can be used interchangeably when you're talking about the derivative. Again, what you're going to see me primarily do are the first three there, f prime, dy dx, maybe y prime. All right, again, depending on the particular situation. All right, so for this section and for the rest of this chapter, anytime we have to evaluate a derivative, we're going to be doing it using the limit definition until we've done enough of them to develop the patterns that we need to figure out the formulas. Okay. All right, so again, I don't know how much of this some of you did in pre-calc. All right, so there are three basic types of functions. Each one has its own pattern for evaluating the difference quotient. The first one is a polynomial. All right, for a polynomial, it's easy to do if you use a step-by-step method. For a rational function or a square root function, all right, we have a slightly different pattern to go through. All right, but regardless of what we've got, all right, there is, I'm just looking to see if there's a better example here than, yeah, okay. All right, there's, regardless of what we've got, it's a matter of filling in the difference quotient and doing some algebra so that you're able to take the limit. Because if you look at the difference quotient the way it's written, right? I can't just plug 0 in for h because that'll give me a 0 in the denominator. So the specific function that I'm trying to find the derivative of, when we plug it in, there's algebra that has to go on to be able to get a factor of h into the numerator so that I can reduce it with the factor of h in the denominator. Then that will let me take the limit at 0. We actually saw some of these problems a few sections ago at the beginning of the limit section. All right. All right, so when we do the instantaneous rate of change, you could do it in general for the function, or you could do it at a specific point. All right, so I'll make sure that I do both so that you see what it looks like. All right, so let's let me start with a polynomial. All right, so let's start with f of x equals, well, let's just do x squared for now. All right, so in order to do this, I need to fill in the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, so in this case, what I'm looking for is the general derivative of the function, the instantaneous rate of change of x squared for any value of x. All right, so I need to basically fill in each piece of this. So if I do this one step at a time, so let me figure out f of x plus h. So that means I'm going to replace x here with x plus h. And I'm going to multiply this out. When I do that, I get x squared plus 2xh plus h squared. And before someone asks me where the 2xh came from, you're multiplying x plus h by x plus h. Do it out term by term, and you'll see where the 2xh comes from. All right, then I need the numerator. All right, so that is f of x plus h minus f of x. Well, I just worked out f of x plus h. It's this. So that is x squared plus 2xh plus h squared minus f of x. So minus x squared. And I want to simplify this however I can. So in squared. All right, so in this case, I have a positive x squared and a negative x squared. So those add to 0. And what I'm left with is 2xh plus h squared. All right, so now I need to put the fraction together. So f of x plus h minus f of x all over h. All right, so again, I work the numerator out. That's what this is. 2xh plus h squared all over h. All right, now on top I've got a common factor of h, so I can take that out. And this is where I get to say I have an h on the bottom and an h on the top, a factor of h on the bottom and a factor of h on the top. So those divide out. I get 1. So that means I'm left with 2x plus h. So the last thing I need to do to find the derivative is take the limit. So now the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, this is this, which is this. So that's going to be the limit as h goes to 0 of 2x plus h, right? And I'm taking a limit. So the thing I always do when I take a limit is I try plugging it in. So I plug 0 in for h, and I get 2x plus 0. So I get 2x. All right, so f prime of x is 2x. Right? So to interpret that, the instantaneous rate of change of the function f of x equals x squared at any value x is going to be represented by 2 times x. So if I want to know what is the instantaneous rate of change or the slope of the tangent line to the curve at 2, x equals 2, I would just plug x equals 2 into the derivative. All right, if I wanted to know what is the slope of the tangent line to the curve at -7, I would just plug -7 into the derivative. Okay. If we take a look at a problem where a specific view is needed, all right, suppose I am asked rather than being asked to find the general derivative, which is what this is. Suppose I have a function. We'll take a different polynomial this time. Let's take f of x equals, oh, I don't want to do that because that's going to be, okay, let's do x squared minus 4. And I want to know what is the slope of the tangent line to the curve, specifically at x equals 3. All right. So what I'm looking for in that case, because I only need that one value, is f prime of 3. All right. So what I can do now is replace the x in the difference quotient up here with 3. All right. So if I'm looking for a specific point, what I'm looking for is the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. All right, and what this is going to do is it will simplify the algebra a little bit, okay? So if I put this through the same steps I did up there, right? F of 3 plus h, so that's going to be 3 plus h squared minus 4. So when I multiply out 3 plus h squared, remember you're doing 3 plus h times 3 plus h. I'm going to get 9 plus 6h plus h squared minus 4. So then I can combine the 9 and the minus 4, and I get 5 plus 6h plus h squared. All right, so now I do f of 3 plus h minus f of 3. So I take 5 plus 6h plus h squared minus f of 3. So f3 is going to be 3 squared minus 4. Okay. All right, so what do I have here? I have 9. 9 minus 4 is 5. So that becomes minus 5. So then I have a plus 5 and a minus 5, so that's 0. So I'm left with 6h plus h squared. All right, so f of 3 plus h minus f of 3 all over h. So 6h plus h squared all over h. I've got a common factor of h here, so I'm going to take that out. Okay, let me get some more room here. All right, so I can factor that h out, reduce it with the h in the denominator, and then take the limit. So I take the limit as h goes to 0 of what I have left here, which is 6 plus h, which is going to give me 6. All right, so f prime of 3 is 6 for this function. So that means the slope of the tangent line to the curve at the point x equals 3 is going to equal 6. Now suppose I want the equation of the tangent line to the curve. All right, let's take this a step further. All right, so if I want the equation of the tangent line to f of x equals x squared minus 4 at x equals 3. All right, well, what do I need to write the equation of a line? I need a slope and I need a point. Here's my slope, right? So this is the slope of the tangent line. Okay, so I have my slope, m equals 6. I need a point. Well, I know the x-coordinate of my point, so now I need the y-coordinate of my point. Right, so my point is going to be 3, comma, f of 3. So that's going to be 3, comma, what do I get when I plug 3 in here? Well, 3 squared is 9. 9 minus 4 is 5. So now I have a point and a slope. Right, so I'm going to come over here to the point slope form for the line, and I'm going to put it all together. All right, so y minus 5 equals 6 times x minus 3. All right, so y is going to equal, let me see, it's going to be 6x minus 18, and then I add the 5 over. So minus 18 plus 5 is going to be minus 13. And this is the slope of the tangent line to that curve at the point x equals 3. Now you could go to your grapher, graph the function, and graph the line, and you'll see what happens. In fact, why don't we do that? The GeoGebra grapher in front of you, hopefully. Still getting used to this. Jeez. Okay, that's interesting. All right, so if I put the function in, right, so the function is x squared minus 4. All right, so there's my function, and my line is 6x squared minus 13. So I'm sorry, 6x minus 13. All right, and take a look. Where does it touch? Touches right here at that point, 3 comma 5. All right, and if I zoom out, well, actually, let me just move it down a little bit. All right, so there's your curve, and there's your tangent line. All right, touches at that one spot only. All right, in fact, if I zoom in, it'll be easier to see that it. Actually, it's not. I'd have to zoom too far in to make that make sense. All right, so you can take your function and you can take your tangent line. You can confirm, all right, that what you've got is the tangent line to the curve. Okay. You can do that on the TI calculator as well. All right, it just doesn't show up on the screen as well as this one does. Okay. All right, so let's put the whiteboard back on. All right. All right, so this is basically our process. Now, there's two other types of functions that you're going to have to deal with here, and that is a rational function and a square root function. And for a rational function, come on, move. Keep an eye on the time. Yeah, we're fine. All right, for a rational function, when you put a rational function together in the difference quotient, you have to combine, you basically have to get a common, here, I'll show you. Easier for me to show you than for me to tell you. So let's just take a basic rational function, 1 over x. So if I want f prime of this, all right, so again, the limit as h goes to 0, f of x plus h minus f of x all over h. All right, now the difference between doing one of these and doing a polynomial is I'm not going to try and do it step by step because there's nothing for me to do at each step. So I'm just going to put this all together. All right, so this is going to be the limit as h goes to 0, f of x plus h. So I replace x with x plus h. So I get 1 over x plus h minus f of x, so f of x, all over h. All right, now we have to reduce this down to the point where I no longer have a factor of h in the denominator. All right, so one of the things I probably mentioned last semester, I don't remember or not, when we were working these problems is how do you know when you're done? And you know when you're done when you can plug 0 in for h. All right, so I can't do that right now. And there's no obvious algebra that I can do based on what this looks like. So what I want to do is I want to eliminate my complex fraction. All right, so I'm going to do the algebra that's kind of staring me in the face. I have a complex fraction, I want to get rid of it. All right, so that's going to involve multiplying the numerator and denominator by the common denominator in the problem. So I have two fractions here. One has a denominator of x plus h, one has a denominator of x. So that makes my common denominator x times x plus h. So I'm going to multiply the numerator of the big fraction by x times x plus h, and the denominator of the big fraction by x times x plus h. All right, so I am going to get then the limit as h goes to 0. All right, so on top, when I multiply this by this, the x plus h's divide out. I have a factor on the top and on the bottom, and I'm left with an x. When I multiply this by this, I have a factor of x on the top and a factor of x on the bottom, so those go, and I'm left with x plus h. So minus x plus h. I don't ever want to multiply out denominators, right? If you took pre-calc with me, you heard me say that 100 million times. Never multiply out your denominators, all right? Always leave your denominators in factored form because you may have to reduce the fraction. All right, now I still have a problem here because I still can't plug in 0 for h because I've got that factor of h. So let's keep going. I'm going to simplify the numerator. So I get the limit as h goes to 0. Now on top, I'm going to do a little fiddly work up here, right? I'm going to multiply through that negative, so I'm going to distribute that negative sign. So on top, I get x minus h. And right here, I have x minus x, so that's 0. Yes, so the top would be minus h. That's exactly right. Minus h over h times x plus h. All right, and then I can do that. So now I'm left with a minus 1 on top. So now I have the limit as h goes to 0 of minus 1 over x times x plus h. And again, I'm at a point where I don't really see what else to do, right? There's no more algebra for me to do. So let me see if I can plug in h. So now if I plug in h, right, 0 for h, I get -1 over x times x plus 0, which is -1 over x plus 0 is x, and x times x is x squared. Okay. All right, so what I get here now is that f prime of x is -1 over x squared. Right? Anytime you have a rational function, it's going to follow that pattern, right? You'll have a complex fraction. You eliminate your complex fraction by multiplying the top and bottom by the common denominator. You simplify that down as far as you can, and you should be able to pull a factor of x on the numerator that will then cancel or divide out with the factor of x in the denominator. And at that point, you should be able to plug 0 in for h. All right. But again, at each step along the way, you have to look, can I plug 0 in for h yet? Can I plug 0 in for h yet? And for this one, the answer is no, all the way up to this very last step here. All right, where all of a sudden, yes, I can, and it doesn't cause a problem. All right, so any rational function is going to look basically like that. All right, so the only other type of function that you would have to deal with is a square root. Okay, so if I have, put a dividing line there. If I have a square root function, again, I'll do a basic square root function because I'm hoping this is not all brand new to you. All right, if I want to find f prime for a square root function, I'm going to follow the same basic path I did with the rational function, because trying to go step by step, there's nothing I can do at each step. So f prime of x is the limit as h goes to 0 of the, hang on. I didn't want to write that yet. F of x plus h minus f of x all over h. All right, so that's going to be the limit as h goes to 0. F of x plus h, I put in x plus h for x. So I get x plus h minus f of x all over h. All right, so I can't put 0 in for h yet because that would give me a 0 in the denominator. There's nothing on top that I can do just with what I have here to simplify that at all. All right, so when I have a square root, what I have to do is rationalize the numerator. What I need to do is I need to get that stuff that's underneath the square root signs out. So to get it out, I have to rationalize it. So to rationalize a square root like this, right, you multiply by the conjugate, top and bottom. All right, normally you would see this if you had square roots in the denominator of a fraction, you would want to get them out of there. In this case, I want to get the square roots out of the numerator. So I'm going to multiply by the square root of x plus h plus the square root of x. Same thing down here. Square root of x plus h plus the square root of x. H. All right, so on top, when I multiply those two together, that's the difference of squares. So I get the square root of x plus h squared, which is just x plus h, minus the square root of x squared, which is just x. And again, on the bottom, don't multiply out your denominator, leave it written this way, that's a plus. Okay. Still can't plug in because I've got an h down here, but up here I have plus x minus x, so those go away. Those add to 0. And I'm left with just an h in the numerator. All right, so I've got the limit as h goes to 0 of h over h times this. And now, I'll do it this way. Those two go away, leaves me a 1 up there. And now what I'm doing is taking the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. All right, and now I'm going to stop and I'm going to try and plug in the h again, like I do at every step. All right, so if I let h be 0 here, I have 1 over the square root of x plus 0 plus the square root of x. Well, x plus 0 is just x, so then I have the square root of x plus the square root of x, 1 over 2 square roots of x. Okay, so that means that prime here is 1 over 2 square roots of x. All right, now we've done a couple of things here, not just look at some basic ways to evaluate the difference quotient, but we've actually come up with a few very specific formulas. Okay, I'm going to move back up. I'll move back down for those of you who are still writing notes. All right, but I want to move back up here for a minute. And come on. And I want to take a look at what I did. All right, so the very first problem we did was f of x was x squared. And we went through, how exactly? Okay. You know what? Kevin, give me just 1 second. Let me work my way back down there and then I'll answer that question, all right? All right, so the very first problem we did was to take f of x equals x squared. We went through this process, right? This whole process of finding this limit and discovered that f prime is 2x. So what does that mean? Well, that means if I have the function f of x equals x squared, then I know its derivative is 2x. So now I don't have to do that again. Okay? So if you see a problem where you're asked to take the derivative of x squared, you've gone through the steps to do that. All right? And you got 2x. So that is the derivative of x squared. All right, so for this one, I can't make any conclusions because that was a specific function at a specific point. But how about this one? 1 over x, right? We started with 1 over x. We went through the whole limit definition and discovered that the derivative of 1 over x is negative 1 over x squared. That means now I know the derivative of that function. I don't have to go through that limit anymore. Okay. Same thing down here for the square root of x. I started with f of x is the square root of x and discovered through the process that the derivative is 1 over 2 square roots of x. Now, Kevin, to answer your question, when you plug 0 in for h, over here you get x plus 0. Right? So x plus 0 is just x. So this is the square root of x plus the square root of x, which is how we get 2 square roots of x down there. Okay, I probably scrolled away from it too quickly. All right, so we are going to derive some general formulas, all right, and we're going to start doing that on Thursday. Okay, but the way we're going to derive those formulas, the way we come up with those formulas, and the way you deal with any sort of derivative where you don't have a formula is using this process right here, which is why you need to know it. All right, to be able to find the derivative of a function at a specific point, all right, we need to have some conditions. There's a relationship between a function being differentiable, that is, you can find its derivative at a point, and a function being continuous. We can find the derivative of a function. All right, wait, how do I want to say this? I want to say this the right way around. There are continuous functions that fail to be differentiable. Okay, so remember, when we talked about continuity, we always talk about continuity at a point. A function can be continuous everywhere, or it can be continuous on intervals. So when we talk about discontinuities, we talk about discontinuities at a point. All right, but we can also talk about continuity at a point. Is a function continuous at a specific value? And we looked at that. We actually looked last time. We did some problems on Monday, and then we did some problems on Thursday about determining continuity at a point. Tended to be we had split domain functions, piecewise functions. All right. A function is being differentiable at a point implies that that function is continuous at that point. However, being continuous at a point does not imply differentiability. All right. So if I have a function that takes a sharp turn, all right, it has, let's say it has something that looks like this. Suppose it looks like that, and then all of a sudden does that. So you've got this point here where the tangent line does something weird, all right, and that is it becomes infinite. All right, if I have a function that, let's say, does something like that, then there's a point here where the tangent line becomes infinite. All right, and if the tangent line becomes infinite, then that means the function is not differentiable at that point. Now we're going to see, all right, we're going to see as we move on how that's affected. Okay, but I just want you to be aware of that. Okay. Some of the applications problems involve split domain functions, piecewise functions. And that point where the function breaks, that gives you that sharp point on the function, is going to be a point where the function may be continuous but won't be differentiable. The velocity of a car, suppose the distance in feet covered by a car moving along a straight road t seconds after starting from rest, is given by the function f of t equals 2t, where t is between 0 and 30. So that is for the first 30 seconds that the car is traveling. So the first part says calculate the average velocity of the car over the time intervals, over the time interval from 22 to 23 seconds, then 22 to 22.1, and then 22 to 22.01. All right, so we can do that. We can do that on the calculator. All right, so let me, okay, let me do that. Let me come over here. So we have, all right, helps if I have the pen, not the eraser. F of t equals t squared, 2t squared, sorry. T being between 0 and 30. All right, so we've got three intervals that we need here, 22 to 23, 22 to 22.1, and 22 to 22.01. All right, so if we look at the average rate of change, All right, so the average rate of change, the difference in the x's over the difference in the y's. All right, so for this first one, the difference in the y's over the difference in the x's, sorry, that was silly. All right, is going to be f of 23 minus f of 22 over 23 minus 22. This one is going to be f of 23 minus f of 22.1. 22, sorry, 22. No, that's backwards, isn't it? Sorry. Come on, move. All right, hang on. I'm having my computer's having an issue. All right, let's try that again. F of 22.1 minus f of 22 over 22.1 minus 22. There we go. F of 22.01 minus f of 22 over 22.01 minus 22. All right, if we drop each of these into the calculator, all right, I'm going to cheat just a little bit here, I think. Hang on. Yeah, okay, so the first one ends up being 90. The second one ends up being 88.2. And the third one ends up being 88.02. Now we can continue with this, and I think what we're going to find as we do is the same thing that happened with the maglev train when we did this process. Each time I throw another 0 in here, it's going to throw another 0 in here. All right, so I can make a claim at this point that I believe that this is probably going to be approaching 88. All right, now the car is moving in feet. The time is measured in seconds. So each one of these is feet per second. Right, feet per second. All right, so I can verify my supposition here by taking a look at the actual speed at 22. All right, so now the second part says calculate the velocity of the car when t is 22. All right, so that is going to be the limit as h goes to 0 of f of 22 plus h minus f of 22 all over h. Again, because we're only interested in this specific point in time. Oh, I went too far with that. I need the function. All right, so f of 22 plus h is going to be 2 times 22 plus h squared minus 2 times t squared. 2 times 22. There we go. All over h. All right, now when I multiply all of this out, okay. Oh, they didn't do it that way in the book. I have to actually do it now, don't I? All right, so let's see. What is 22 squared? Hang on. What is 22 squared? Clear. 22 squared. 484. All right, so this becomes the limit as h goes to 0 of times 2, 968, plus, then I do 2 times 22 times h, so it's going to be 44h, times 2 again, so that's going to be 88h, plus h squared, minus 20 squared, which is 484, times 2, which is 968, all over h. All right, so again, I've got a positive and a negative one of those, and I can factor in h out of the numerator. All right, so I get the limit as h goes to 0, h times 88 minus h over h, and then those go away, and I take the limit as h goes to 0, I get 88. Okay. All right, so when we compare the two processes, all right, finding the average rate of change as we let 23 approach 22, right? As we get closer and closer to 22, it appears that we're getting closer and closer to 88. And as it turns out, that is actually what the instantaneous rate of change is. So the speed of the car at 22 seconds is 88 feet per second.